Good morning, friends. We are learning magnetic properties of the solid unit number 5 for the BSc third year semester 6. In this lecture, we will discuss the hysteresis of the magnetic material. Hysteresis is a special property which is assigned to which is the inherent property of ferromagnetic and ferrimagnetic material. The ferromagnetic material. The speciality of the ferromagnetic materials is the presence of domains in it. Due to these domains, when we apply an external magnetic field, the magnetization is stored in the magnetic field, and when we remove the magnetic field, that time quickly the magnetic field does not remove. It requires certain amount of time to remove the total magnetic field from the magnetic field. This means when we remove the external magnetic field, suddenly the magnetization in the material is not zero. Okay, the hysteresis here refer to the lagging of the magnetization of a ferromagnetic material like iron. This means when we apply a magnetic field and as we remove the external magnetic field, that time in paramagnetic material, the magnetization inside the material is quickly zero. But in case of the ferromagnetic material, the magnetization does not zero quickly. It is lagging the magnetization. In another word, when the magnetic material is magnetized in one direction, it will not reflex back to the zero magnetization even when the imposed magnetizing field is removed. Hence, it has to be driven back to zero. A field in the opposite direction needs to be applied. For studying the magnetic hysteresis, we will apply we will see the BH curve. Here, if an alternating magnetic field is applied to the material, its magnetization will trace out loop called as the hysteresis loop. And this study is well supported by the Wish domain theory. In the next slide, we will see the BH curve. This is the BH curve. Here, this is the B is the magnetic flux density, and this is the magnetization force. Here, this is the magnetization force. Sometimes it is also called as the magnetic field intensity, and this is the magnetic field. Here again, this is the curve in between B and S, so it is called as a BH curve. Here you can see that this is at a zero. Here we have at a point, I have considered here this point. At the pointed point, suppose you are at this point and you start the application of the external magnetic field. Let us suppose a zero magnetic field is applied to the ferromagnetic material, and if we increase the magnetization force here, if we increase the magnetization force along the x-axis, if we increase the magnetization force, then this graph going to increase slightly, like this. The graph increases as the magnetization force increases. This graph is increases like this. Again, as we increase this magnetization force, as the magnetization force increases, the magnetic flux density increases. At this point, here you can see, at this point, at this magnetization force, you get the flux density like this. This is the flux density at the magnetization force here. Okay, this is an application of an external magnetic field. At the point A, if we try to increase again magnetization force, then the magnetization flux density does not increase. This point A is called as a saturation point. This means saturation point means even if we have increased the magnetization force, the flux density in the material does not increase. This is a saturation. This means here the curve going to flat. This is the flat. From here, curve is going to start flattening. Therefore, here the magnetic flux density remains constant, and the total magnetization remains constant in the ferromagnetic material. Therefore, this point or point A is called as saturation point. Now, why this happen? You know, In case of the ferromagnetic materials, there are numbers of domains. These domains are responsible for the creation of the magnetization inside the ferromagnetic material. As there are numbers of domains, and the magnetic field vector or magnetization vector in a particular domain is having a particular direction. Therefore, if all the magnetic domains align in a particular direction, which is equal to the external magnetic field, this means all domains get magnetized. And due to this all magnetic domain magnetization, the total material is completely magnetized. And more than that, if we apply the magnetization force, then there is no chance to development of the magnetic field inside the material. Therefore, there is a creation of the particular field that is called as saturation. Particular condition, that is a saturation. Now, here from the point A, let us assume that if we remove the external magnetization force, that is, here we are trying to go backward from magnetize this point here, this point to this point here. As we trying to go this that direction, then this should be go like that way. This means if we try to apply the external magnetic field, remove the magnetic field here, initially as we apply the initial magnetic field, this curve go like this. But when we remove the external magnetic field, this curve should not coming like this. But this curve should be comes like this. But here, as we remove the external magnetization force from this point to this point here, you can see this point to this point, then this curve going like this. That is flux density curve going like this. This is the flux density. Here, you can point out here, it is a flux density. From this point, this is a particular flux density at the highest magnetizing force. And if we trying to decrease the magnetizing force from highest point to the zero value, this curve comes like this, and this is to the point B, and you can see here that at point B the magnetization force is zero, but the flux density B is always remain inside the ferromagnetic material. This is the B from 0 to B. This value is all remain when we try to decrease the flux density. As we have seen in first slide, that if we remove the external magnetic field, the magnetization does not equals to zero inside the material. This means here this is the remain magnetization. This is called remain magnetization. And here this point B is called as the retentivity. This point B is said to be the retentivity. Here you can see if H is reduced to zero after saturation, it has been detached in the positive direction. This is reached in the positive direction. Then induction in the ring specimen, this ring specimen nothing but the magnetic material, iron material, will decrease from Bs to Br, called as the retentivity or residual induction. Here you can see here again. This is point. When driving force of magnetic field drops to zero, this is a magnetic field drop to zero here. The ferromagnetic materials retain a considerable degree of magnetization. There is a magnetization here. You might not confuse between M, H, or this one. This is a magnetization, and there is a relation between magnetization and magnetic field intensity and magnetic field B equals to mu 0 H. And this is the magnetization. This magnetization is the magnetic field intensity inside the material due to an application of the external magnetic field. Suppose you have applied the magnet to the ferromagnetic material, then this due to the presence of external magnetic material, this magnetization is induced inside the ferromagnetic material. This is nothing but the induction of the magnetization. As there is an increase the magnetization inside the material, this means that there is a creation of the magnetic material, magnetization inside the ferromagnetic material. Okay, but here you can see that as we decrease the magnetic field intensity here. This is the magnetic field intensity here, but the magnetization inside the ferromagnetic material does not equal to zero. Here, this should be the this come like that, this one, but this coming to this one it will be equal to this. This remains. This is called zero to this value. 0 to this is the remain magnetization, and this is remains inside the ferromagnetic material. And this is the considerable degree amount of the magnetization. This is the considerable amount of the magnetization. Therefore, this magnetization remains. This is called as a remain. And here, if we try to decrease the magnetization inside the ferromagnetic domain, then we have to apply the negative magnetic field intensity. Here, we are from applying here 0 to minus h. This means here if we apply the 0 to minus h magnetic intensity, then the magnetic material magnetization will be equal to 0. Okay, the driving magnetic field must be reversed and decreased to large value to drive the magnetization 0 again. Okay, here the magnetization in the material will be equal to 0. Here again, this is the resistivity, and here this is the coercivity. Here coercivity nothing but the negative magnetization. This is the negative magnetic force. Coercivity is nothing but the negative magnetization force here, and here is the remain retentivity. This is the coercivity. This coercivity nothing but the zero magnetic flux density or zero magnetization inside the ferromagnetic material at the negative magnetic force, negative field intensity. Okay. Here again, if we decrease the magnetic force, and this decrease the magnetization force again here, and here this is the saturation opposite direction. That is again the saturation, and this again we decrease the magnetization force. The magnetic field does not, magnetic field density does not increases more, but it's going to the, and here we will again take the positive direction of the magnetization force. This is going to be increases here, and here again this is going to be increasing magnetization force, and it's going like this again going to the saturation. This means this part is called as a storage of the magnetization. This completely part is called as a storage of the magnetization, and this storage of the magnetization due to the particular property of the ferromagnetic material is called as the ferromagnetic domains. This is called as the ferromagnetic domain. This is the hysteresis of the ferromagnetic material. Thank you.